All right, diving in, we're tackling some excerpts today from this seminar, from development to function. It's all about how our brains develop and how they work, especially with vision. We're going to ponder some really interesting questions like, why does our eye seem backwards, designed backwards, compared to a camera? How do those limitations from evolution affect our brain's wiring? And what can we learn from things like spandrels in nature? Plus, we'll dig into how the idea of algorithmic growth applies to both evolution and how we learn.
I am very excited to unpack all of these concepts. Really, it's amazing how complex and adaptable the brain is.
Right. One of the things that really stood out for me was the discussion about the human eye, how our retina is backwards compared to a camera. It just seems so counterintuitive that light has to travel through all these layers of cells before it even hits the photoreceptors, all the way at the back.
It does seem counterintuitive in a camera. The sensor is positioned right at the front, so it can capture light directly. But our retina, the human retina, this backward design, is a result of evolution. It all stems from how the tissues folded, way back, our ancestors' embryonic development. And that folding essentially locked in this particular structure for the eye.
So we're stuck with this quirk because of an ancient fold. That's fascinating and strange, isn't it?
It is. It really underscores an important aspect of evolution. It can only work with what's already there. Each step builds upon the previous, even if it ends up with solutions that seem less than ideal. Imagine our spines. They're still evolving, but they're not going to just suddenly transform into exoskeletons because they have this long evolutionary history behind them.
Like trying to renovate a house without tearing the whole thing down first. You're limited by what's already there, the structure. You can't just magically change everything.
That's a great analogy. It's like evolution is always, making do, working within the constraints of what came before.
So we carry these echoes of our evolutionary past, even in complex structures. Like the eye, makes you wonder, how much of the brain's wiring is a direct adaptation and how much is just a result of its developmental history?
That is a great question. And it leads us to two fascinating concepts from Stephen Jay Gould, the evolutionary biologist: spandrels and exaptation. Think about architectural spandrels in a building like the Basilica di San Marco, those triangular spaces created where arches meet, rectangular frames. A lot of times these spandrels are beautifully decorated with art, but they weren't originally intended for that artwork. They were just a byproduct of the arch's structure.
Oh, I've seen pictures of those mosaics in the Basilica. They are breathtaking.
So you're saying that in biology, features can just emerge as side effects and then become useful for something totally different.
Exactly. Gould used this analogy to explain biological features that arise as side effects of other adaptations and are then, later co-opted for new functions. This process is called exaptation. That is so resourceful. Evolution, something that starts as a mere byproduct can end up with a whole new purpose. But how does this apply to the brain?
It makes you wonder how much of our brain wiring could be a spandrel, a consequence of development.
Yeah.
That evolution has repurposed for a different function. A perfect example is cortical columns.
Those vertical structures that run through the cortex, but aren't those essential building blocks of how the brain is organized?
Well, they are often described that way, but whether they're functionally necessary is actually debated. Consider squirrel monkeys. Some have anatomically distinct cortical columns, while others don't. But there's no difference, it seems, in their vision.
So you're telling me these monkeys, they can have different brain structures and still see perfectly fine. That's wild if those columns, if they aren't necessary for vision. Why are they so common?
That's the interesting part. One possibility is they emerged as a side effect of making developmental processes more efficient, for instance. Having neurons organized in columns might make it easier and faster for them to connect with the right partners during development. You think about developmental efficiency, not functional necessity.
It's like those 6 photoreceptor neurons in the fly visual system we talked about before. That precise wiring might be a developmental constraint, a way to ensure efficient connections during development, rather than a functional requirement for vision itself.
Exactly. And this brings up a very interesting question. Are cortical columns truly essential for visual processing? Or could they be a spandrel, a side effect of development that's been, exapted for some other purpose, maybe a higher level purpose?
This makes me wonder how many features of the brain might have started as just happy accidents, but if they aren't essential, what other functions could they serve?
That is a question researchers are still exploring. this possibility that even fundamental brain structures could be spandrels really underscores the brain's incredible adaptability. And it leads to another intriguing idea, the brain as a memory prediction system.
Okay, now this is where it gets really interesting. I'm all ears. How is this memory prediction model different from
the way we usually think of computers?
Well, traditional computers store information in specific locations, like files. In a cabinet, you access them by going to that exact spot, that address. But the brain doesn't seem to work that way. The seminar suggests that it's constantly predicting what's going to happen next based on past experiences, less like a file cabinet, more like a constantly updating prediction machine.
So instead of storing specific data points, it's more about recognizing patterns and making predictions, like trying to figure out the next note in a song based on the melody so far.
That's a great analogy. Jeff Hawkins, who's a computer scientist and neuroscientist, proposes that. This is how the neocortex works. The neocortex is the outermost layer of the brain. And the neocortex handles complex functions, right? Like language, reasoning, planning.
Exactly. Hawkins argues that it's essentially a massive memory prediction machine. It stores memories sequentially and in an auto-associative manner. And it uses these memories to make predictions about the world.
So I'm curious, what does it mean for memories to be stored sequentially and auto-associatively? Could you break those down for me?
Sure. Think about trying to sing a song backwards. It's incredibly difficult because our brains store memories in order. Sequentially, each memory is linked to the one before it, like creating a chain.
Ah, that makes sense. So each memory is like a link in a chain, and the order really matters. But what about auto-associative? What does that mean?
It means that even a small fragment of a memory can trigger the whole memory. Think about recognizing a face, a familiar face, even from a blurry photo. Your brain is using that partial information to activate the entire memory of the person.
So our brains are filling in the blanks, making connections, predicting what's coming next based on these chains of memories. That's incredible, this model. This has some pretty big implications for how we think about learning and memory, doesn't it?
It really does. And that leads us to the seminar's discussion of algorithmic information storage and how that relates to these processes.
I am eager to dive deeper into that. Sounds like we're about to uncover even more amazing insights about how our brains work.
So the seminar suggests that memories might not be stored as like static data points, but are delestia. Algorithmic information is the rules to recreate them.
Algorithmic information, that's a new one. So it's not the actual data that's stored, but the instructions for how to reconstruct it, like having a recipe instead of the finished dish.
That is a fantastic analogy. It implies that storing a memory and retrieving it are deeply connected. Every time you remember something, you're all to take. Changing it slightly, it's not like pulling a file from a cabinet. It's more like reweaving a tapestry each time you access it.
Whoa, that's mind-blowing. So it's not about finding the neuron that holds a specific memory, but understanding the network patterns that create it.
Exactly. Each time you recall something, it reshapes the memory subtly. The seminar uses the example of a PIN code. The digits might stay the same, but the context, the feelings associated with the memory could change over time.
Yeah, that makes sense. I might remember my PIN code, but the memory of where I was when I first memorized it or how anxious I felt the first time I used it, those details might shift or fade. So if memories are like recipes constantly being rewritten, how do we learn new things?
The seminar emphasizes that learning and memory are all about training the brain, changing the network by making new associations. It's about actively shaping the connections between neurons.
So it's not just about the input, but how that input changes the existing network. It's like learning to play music, a musical piece. The memory isn't just a bunch of notes stored somewhere. It's accessed through playing, the physical act of playing, the feeling of your fingers on the instrument, the coordination of movements.
Precisely. Yeah. The memory is embedded in the whole process, which brings us to a fascinating question about memory storage. How does this relate to the idea of grandmother neurons?
Right. Like there's one neuron that fires every time you see your grandmother's face. Does that actually... Hold up.
This algorithmic model challenges that notion. It suggests that memories are more likely spread across the network, not localized in single neurons, even if one neuron seems really active. When you recall a memory, it's probably just one part of a bigger web of interconnected neurons.
That makes the brain's resilience even more impressive. If one neuron gets damaged, the whole memory isn't lost because the network can compensate reroute, reweave itself. Memories might change a bit, but not completely disappear.
Exactly. That robustness is key to the brain's design. But this discussion of memory and learning makes me wonder, how does the brain decide which connections to strengthen, which pathways to reinforce? It can't be completely random.
Right. That's a great question. There must be some guiding principle at play. What does the seminar say?
This is where it gets even more fascinating. The seminar talks about neural Darwinism. It's a concept proposed by Gerald Edelman.
Neural Darwinism. So now we're applying evolutionary principles to the brain. How does that work?
Edelman saw parallels between the brain and the immune system. He argued that both rely on selection and competition. Like the immune system generates a bunch of antibodies. Each one recognizes a specific pathogen. When a pathogen enters, the antibodies that combine to it are selected and amplified, while others are eliminated. Survival of the fittest at the cellular level.
It's like a constant arms race between the body and invaders. The immune system adapting to meet the challenges. But how does that apply to the brain?
Edelman argued a similar process happens in the brain. Throughout our lives, he proposed 3 stages of neural Darwinism, developmental selection, experiential selection, and reentry.
Okay, would you break that down for me? What happens in each stage?
In developmental selection, initial brain wiring is shaped by genetics and early experiences. This creates diverse neural connections. Then, experiential selection kicks in. Frequently used connections get stronger, while unused ones weaken, use it or lose it for the brain.
So our experiences are constantly
sculpting
the connections in our brains.
Exactly. And that leads to the third stage, reentry. This is the ongoing recursive interaction between different brain regions. It's a constant conversation happening inside your brain. Imagine seeing a delicious cake. Your visual cortex processes the image. Your memory recalls past experiences with cake. And your emotional centers light up with anticipation. All these areas communicate and integrate information to shape your experience.
So it's not a one-way flow of information, but a constant back and forth between different areas. Fascinating. But how does neural Darwinism explain how the brain strengthens specific connections?
Edelman said, it's all about competition and selection. A new experience triggers a wave of activity, activating various neural circuits. The circuits that resonate most strongly with the experience are the ones selected and strengthened.
So it's almost like the experience is choosing which pathways to reinforce.
In a way, yes.
Right.
Remember, the face recognition neuron we talked about, it wasn't pre-programmed to recognize a specific face. It was selected by the experience of seeing that face through the activation patterns that spread through the network.
So it's a self-organizing system, constantly evolving based on our experiences. Like we're sculpting our own neural landscapes through our interaction with the world. But does that mean we can intentionally shape the brain's development?
That is a big question.
Yeah.
The brain isn't a blank slate that we can just program at will. It's a product of evolution and development shaped by countless factors beyond our conscious control.
But we're not powerless, right? There must be ways to influence this process.
Absolutely. By understanding neural Darwinism and the role of experience, we can create environments that foster learning, encourage plasticity, and promote cognitive health. We can play the game strategically, so to speak.
So it's about understanding the rules of the game and making choices about the experiences we expose ourselves to. But this raises another question. If both development and function of the brain are based on algorithmic rules, how does that fit with free will, conscious decision-making? Are we just slaves to our algorithms?
Now, that's a question that's been debated for centuries.
Yes.
Seminar doesn't give a definite answer, but it definitely gives us a lot to think about, it seems like. This incredibly complex system might be governed by rules, but the way those rules play out, it's incredibly intricate and dynamic.
This deep dive has been incredibly stimulating. It's amazing to consider the brain as a self-organizing system, constantly evolving based on experience. It really highlights how much we still don't know about this incredible organ.
It really does. And the seminar emphasizes the importance of seeing the brain through the lens of evolution and development. Understanding its history helps us appreciate its present capabilities and imagine its future potential.
I'm still trying to wrap my head around this, that memories aren't fixed, but they're like constantly evolving algorithms. It's like our brains are these giant prediction machines, always trying to anticipate what's next based on what we've experienced.
And that prediction process, it's not just conscious thought, it's happening all the time at every level of brain function, from how we process sensory information to motor control, even decision-making.
So we're not just predicting what'll happen around us, but also how our own bodies will react and how our actions will play out.
Exactly. It's a constant feedback loop between perception, prediction, and action. And that loop is shaped by the patterns we've encountered in the past.
This makes me think about learning new things. Like when you first learn to ride a bike, it feels awkward, uncoordinated. But then with practice, it becomes almost effortless, like your brain has figured out the code for balancing and steering.
That's a great example. Learning isn't just about getting information. It's about refining the brain's predictive models. As you practice, your brain gets better at anticipating the sensory feedback, the motor commands, the sequence of events, and this lets you perform the skill more smoothly, efficiently.
So it's not just memorizing steps, but training your brain's prediction engine to anticipate and respond correctly.
Exactly. And this changes how we think about education and training. We should focus on creating experiences that challenge the brain's predictive models, force it to adapt, and refine its algorithms, not just rote memorization.
So more hands-on learning, more active problem solving, more chances to test and refine our predictions.
Exactly. And this brings us back to neural Darwinism. Remember, it's not about passively absorbing information. It's about actively engaging with the world, letting our experiences shape the connections in our brains.
It's like we're constantly sculpting our own neural landscapes through our interaction with the environment.
That's a beautiful way to put it. And this sculpting doesn't stop in childhood. The brain stays plastic throughout our lives, capable of adapting and changing based on new experiences.
It's good to know. It means we're not stuck with the wiring we're born with. We can keep learning, growing, evolving throughout our lives.
Absolutely. This plasticity, this ability to change is what makes the brain so remarkable. It's not static, it's dynamic, a self-organizing system, constantly adapting to the challenges and opportunities we face.
I'm feeling a new sense of awe at the complexity and the resilience of the human brain. I'm also feeling a sense of responsibility, knowing that we have some control in shaping our own neural destinies.
That's a powerful insight. By understanding the principles of brain development and function, by being aware of the experiences we expose ourselves to, we can cultivate cognitive health, promote lifelong learning, and maybe even influence the evolution of our own brains in a positive way.
It's a little daunting to think about the brain this way, but also really exciting. It opens up so many possibilities for how we approach education, healthcare, even our own personal growth.
I agree. It reminds us that we're still on this journey of understanding the brain. There's so much we still don't know, so many mysteries to uncover. But with each new discovery, we get a deeper appreciation for the intricate beauty and the limitless potential of this incredible organ.
Well, we've reached the end of our deep dive into the algorithmic nature of evolution and the brain. We hope you've enjoyed exploring these ideas with us.
We encourage you to keep thinking about the implications of these ideas for your own life and to embrace the ongoing adventure of understanding your own amazing brain.
Until next time, keep those